look up like these. Yeah. Is it? All right, good morning, guys. If you have any problems hearing me, please let me know. Hopefully everything's good on your end. The grades have been posted. If you have any questions, comments, problems about any of those grades, we can talk about that. That's perfectly fine. I will be going over that test in detail once we've talked about today's lecture, because today's lecture probably won't take the whole time. So we can do that. On Friday, not only will we be doing the gases lecture, which is the first part of the stuff for exam 3, but we can also do some review for exam 2. So that's kind of where we're at. I think we're in a decent place. So if anybody's got any questions, comments, problems at this point, I'm happy to hear them. Otherwise, I'm about to get started. Okay. So, what are we going to be talking about today? Well, today we're going to be talking about VSEPR, which is valence shell electron pair repulsion. That's what that stands for. VSEPR is what determines for us the three-dimensional geometry of the molecules that we're looking at. And as we move forward talking about reactions and how these things happen and things like that, we need to understand that geometry because it has a big role in how fast those things happen, how easy it is for that reaction to occur. Those are things that we don't really talk about yet, but it's important to be able to understand that structure so that we can talk about those topics. So that's why we talk about that here. There you'll see the list of molecular geometries that we're going to talk about. It looks intimidating. I understand that, but I don't think it's as bad as it actually looks. We'll talk about why I think that in a little bit. But that's what we're going to be talking about today. But first, we need to go back a little bit and talk about what we did in the Lewis structures. So let's talk about the molecule ClF3. So if we want to talk about ClF3, that molecule contains 1 chlorine and 3 fluorines. And if we want to draw a Lewis structure for that molecule, we need to look at the number of valence electrons that are present on both of those species. So if we look at the chlorine, we know that he's here. And so in that row, we see that he has 1, 2, 3, 4, 5, 6, 7 electrons in that outermost row. So he has 7 valence electrons. Okay. When we talk about fluorine, given that he's in the same position, he also has 7 in that row. So 1, 2, 3, 4, 5, 6, 7. So both of them have 7 electrons that we're going to be dealing with. That's the number of valence electrons they have, i.e. the number in the outermost row of that material. 1 chlorine with 7 valence electrons, 3 fluorines with 7 valence electrons. So I have a total of 28 electrons that will need to be distributed in this particular structure. Okay. The next thing that we look at, and the next step that we take after figuring out how many valence electrons there are, is we put this molecule, the structure of it, together. Now, Cl being written first, he's going to be in the middle. So Cl goes in the center. I'm going to put 3 fluorines around him. At this point, it doesn't matter where we put them. I know that there has to be some connection between each fluorine and each chlorine. So I'm going to draw 1 bond in between them all. Those bonds, that line, contains 2 electrons. So given that I have 2 electrons in each, that means I have 2, 4, 6 that I've taken and used. So that leaves me with 22 electrons that I need to distribute around the remainder of the molecule. Okay. And the next thing we have to do after we've drawn our preliminary structure and our bonds is to fulfill the octet rule for our exterior molecules. So everybody's looking to have 8 electrons around them. That's our goal. And that's because if we do that, then we'll be just like a noble gas. Because if you look at these noble gases right out here, there are 1, 2, 3, 4, 5, 6, 7, 8 electrons in the valence shell for any noble gas. And so since we're always talking about, I want to be the noble gas, I'm looking to get the same electron configuration. Now, I may not be able to do that by transferring electrons. That's not what we're talking about right here. But I am going to be able to do it by sharing. And so that's my goal, is to get that 8. So I fulfill the octets on the exterior first. So each fluorine is going to get 2 4, 6. And we try to put them in pairs, but that's just because that's the way they tend to exist. And if I put 6 on each, that gives me a total of 8 around each, because I have the 6 in the lone pairs. So 1, 2, 3, 4, 5, 6, 3 lone pairs, 2 electrons each. And then I have access to the 2 electrons that are in here. So each fluorine now has access to 8 electrons. So they're all happy. That's awesome. 6 times 3 is 18. So that means that I have 4 electrons that are left that still need to be distributed in this molecule. Okay. If I take a look at that, then what I can find is that those 4 electrons go on my central atom. So I put them here and here. Now again, it doesn't really matter where I put them at this point. We'll talk about where things exist later today. Okay. But for right now, I'm just putting them there so that I know that they're there. I need to be able to see that those pairs exist there and that there are 2 pairs. So that's why I put them together as 2 pairs. Okay. That takes care of the other 4 electrons that I needed to distribute. And so now all of my electrons have been distributed. Cool. That's the first part. The next thing that I need to look at is, 1, do I have an octet for everybody? My fluorines have an octet. My chlorine actually has access to 2, 4, 6, 8, 10 electrons. So that is considered a violation of the octet rule because there are more than 8 electrons around chlorine, but that is okay. Okay, because of where he is, he can do that. So having those there is perfectly fine, but we've met the octet rule. Okay, that's the primary. The other thing we have to look at is this thing we talked about at the end last time, which is formal charge. And we'll consider formal charge for fluorine and for chlorine. And we have to consider them separately. Sometimes we have to consider like some of the fluorines differently than others. If their bonding is different, we have to calculate formal charge differently for them based on that bonding. But all of these are bound the same way. So right now I don't need to do that. And the way we talk about the formal charge is to look at how many electrons this guy brought to this party. So each one of them brought 7. Remember, we talked about that previously. They had 7 valence electrons that they brought. So both of them are looking to have access to 7. And when we talk about formal charge, we talk about electrons a little bit differently than we did about talking about the octet rule. When we talk about the octet rule, both electrons in this bond are considered available to fluorine. Okay, that's awesome. But when we talk about what's assigned to fluorine, we cut that bond in half. And we say that one of those electrons belongs to chlorine and one of those electrons belongs to fluorine. Now, is this real? No. This is just bookkeeping. It's a way for us to keep track of, is this a happy place for these electrons to be, or do I need to move them around? That's all this is. Okay? This is not a real charge. It's not based in anything. It's just a bookkeeping method. Now, if I do that and I give this electron to fluorine, then I have 1 electron there, 2, 3, 4, 5, 6, 7. Each fluorine has 7 electrons. That means there is no formal charge for the fluorine. If I look at my chlorine and I cut each of these bonds in half so that we have 1, 2, 3 electrons from the bonds, and then 3, 4, 5, 6, 7, cool. We also have 7 there. And that's no formal charge. So nobody has a formal charge, okay? Typically, we don't necessarily use the squiggly lines. We don't necessarily leave them, but I'm fine if you do. They're just a way for us to keep track of who goes where, all right? Now, there is a formula that you can use to calculate formal charge, and that says that we have our valence electrons minus 1/2 of our bonding electrons minus the non-bonding electrons. So that would be the 7 valence electrons minus 1/2 of the bonding electrons. This bond contains 2 electrons, minus the non-bonding, 2, 4, 6, which also gives me 7. 7 that we're taking away from that, which is 0. So it's the exact same math. It's just a different way of looking at it. Okay, so either one of those works. I tend to find that people are easier with the counting over here as opposed to the mathematics. So that's why I tend to present it that way. But both of those work. And if you're more comfortable with that calculation down here, that's perfectly okay. That's the way I handled it when I was a student. but I do find that most people are not as comfortable with that. Now, questions, comments, problems about that part? Okay, so we've answered our formal charges. There's no formal charge. That's our Lewis structure. How many bonds exist? There are 3 bonds. I see 3, one between each fluorine and the chlorine. Okay. How many lone pairs are on chlorine? There are 2. So this set right here and this set right here. So I have 2 lone pairs on the fluorine. And then it says, what is the electron geometry of this material? And I hear bells going off and people said I don't know what that means. No, you don't, not yet. So this is sort of review, sort of not review. And the reason that I do it in this fashion is because you need to know that those Lewis structures that we just did are entirely important to doing the VESPR. We have to have a Lewis structure and know those formal charges before we can move forward. So that's why this is done this way. Now, electron geometry, molecular geometry, and the bond angles is what we're going to be talking about today. I'll come back to this slide after I've introduced a few things to show you what that looks like. Questions, comments, problems at this point? Okay. So now we're going to get into that 3-dimensional geometry. Okay. So valence shell electron pair repulsion. Again, the valence shell is the outermost electron-occupied shell of the atom and contains the electrons that are usually involved in bonding. Now, when we talk about double and triple bonds, they are considered to exist in the same space as a single bond. So if I have a double bond that I've drawn in a Lewis structure, I only consider that as one bond. If I have a triple bond, I consider that as one bond. And that's because physically they have to be in the same space. Okay. And they take up slightly more space, but we consider them as if they don't. Okay. It's not that big of a deviation. If you have 2 or more resonance structures, which we saw for the BrO3 minus that had 3 that we drew, we can use any of them to determine the geometry. Formal charges are not shown when we do the geometries. We may be asked to calculate them, but they're not part of what we use to determine that geometry. To determine the geometry of a molecule, we need to be able to answer 2 questions. How many bonds are on the central atom, and how many lone pairs are on the central atom? And the idea of valence shell electron pair repulsion is that all of these electrons that exist around this central atom want to be as far away from each other as possible. There is repulsion between those electrons. They're all negatively charged, so they don't want to be that close to each other. So we want to get the best 3-dimensional arrangement to maximize the space between them. That's what this theory is about. Okay, so we need to know how many bonds and how many lone pairs. Okay, and here's this table, and it's sideways, so it's not that easy to see. I'm going to pull over the table that you're going to get on the test. This is not in your exam handouts, but it will be available to you on the text. That should make you feel better about this because you don't need to remember what the electron pair geometries are called, what the actual molecular geometries are called, how many bonds, how many lone pairs, none of that. But we do need to talk about what this table says. So what we see over here, number of electron pairs around central atom. And you'll see that this is split into 2 types. One is bonding, one is lone. Okay, so we need to know how many bonds there are. And we need to know how many lone pairs there are. Okay, there's an example of that type of molecule over here. All right, so that's something that you can talk about. Look, there's ClF3, the one we were just talking about. And notice it says 3 bonds, 2 lone pairs. That's exactly where we are. Okay, you'll see the bond angles listed next. Okay, for this particular molecule, we're talking about approximately 90 degrees. And then we have 2 names. One is the electron pair geometry, and the next one is listed as the geometry of atoms, which is also called the molecular geometry. So this is also termed molecular. Right there. Show you that in just a second. So that's our molecular. You'll see a drawing of the 3-dimensional shape. One of the things that you'll notice about this is that the lines that are just solids are flat. Anything that has a dotted line goes in the back. Anything that's a much bolder line comes out at you. So that's what that 3-dimensional thing looks like. When you do the virtual lab for this, you'll get an opportunity to see in 3 dimensions what these things look like. you'll build a structure and you'll turn it around so that you can look at all of it. Okay. It's important that you get some sense of what that looks like. And then it'll tell you that it's this type. We're not going to talk about the type, but this is something that you'll see if you're on the internet looking at it somewhere else. It may be talking about the type that it is. Okay. So that's what that's for. When we talk about our CLF3, it's listed as a trigonal bipyramidal. Okay. So its overall shape for 5 pairs around it is trigonal bipyramidal. Give me 2 seconds. But I know that 2 of those are lone pairs. And so when we talk about the molecular geometry, I'm not going to be looking at all 5 of those things. I'm only going to be looking at 3 of them. And so I want to talk about the structure that exists for those 3 bonds that are left. And so what happens is that those lone pairs, just like I drew them, are on the same side of the molecule. And then we have our 3 bonds that look like this. And if I had to try and describe that structure, I might describe that as a T. And so that's called T-shaped. Okay, so that's where that name comes from. The molecular geometry does not take into account the lone pairs. My electron geometry takes into account all of them. So that's the difference between the 2. So you'll see that there are many structures that are listed as an electron pair geometry of trigonal bipyramidal, but they have a different molecular structure name. Okay? And that's because not all of those are actual bonds. So when we come back here and we look at our questions again, my electron geometry, as we just said, was trigonal bipyramidal. My molecular geometry is T-shaped, and the bond angles that were given in that table are approximately 90 degrees. Now, why it's approximate, we can talk about that. It has a lot to do with the fact that the lone pairs take up slightly more space than bonding pairs because they're not, in between 2 things. That's a thing. If you need to know about that, you'll get talked to about it. So I wouldn't worry about it too much now. We just want to know that it's approximately 90 degrees. Some classes will ask you what that distortion is, how big that is. I'm not going to be asking you about that, but it is something we can talk about if you're curious. Okay. So that takes us through not only what we did last time, but also what we're going to be doing this time. And so what we're going to do is look at the same molecules that we talked about yesterday for a lot of these and assign them their electron geometry, their molecular geometry, and talk about their approximate bonding. Okay, so questions about that? Yes, this is the molecular geometry. Oh, that one's in the other order. Sorry, molecular geometry is listed over there. Okay, but so like I said, that one that I just showed you is the one that you'll get on the test. So if you want a copy of that, I could send it to you so you can look at it so you know exactly what it looks like. So there you go. So rules for molecular geometry, fairly simple. I'm going to draw the Lewis structure. So I need to remember the rules for drawing my Lewis structure. I'll determine the number of bonds on the central atom. I'll determine the number of non-bonding pairs, the lone pairs in the central atom. And I'll use the table to determine the name of the structure. That's it. I'll say that's it, like it's so easy. All right. Now remember, when we're talking about electron versus molecular, the electron configuration takes into account all sets of electrons around the central atom. That determines the shape the electrons take around that central atom. So that maximizes the repulsion or the spacing between them to minimize the repulsion. Okay. It's also considered the parent structure for the geometry, and we call that electron geometry. We refer to it sometimes EG. When we talk about molecular geometry, we're only talking about the molecules, right? So once you have the electron geometry, we look to see how many pairs of electrons are lone pairs and take those out when we talk about that description. So the number of lone pairs will determine the molecular geometry, also called MG, molecular geometry. Okay. So again, we can have many things that have the same electron structure, but they don't have the same molecular geometry. So we start at the beginning of our table. And the first thing that we talk about is a linear structure. So remember, we consider our double bonds as single things. So if I look at this molecule with carbon right here and the two oxygens on either side has two sets that I need to talk about. So I have two bonds, given that the double doesn't matter. So I have two groups that I have around that carbon. They're both bonding. There are no lone pairs. So the approximate bond angles are 180 degrees, and this is called linear. So that's my linear structure. If anybody has any questions, feel free to yell out. When we talk about trigonal planar, okay, as our base structure, we have three electron groups, 1, 2, 3. I have a BF3 here that has 3 bonds between the boron and the fluorine. All of those are bonding pairs. So my electron geometry and my molecular geometry are exactly the same, trigonal planar. My approximate bond angles are 120 degrees, and this exists on a flat plane. All 3 of them are on this plane. Okay? So 120 degrees in between them, trigonal planar for both my electron and my molecular geometry. Then we get to bends. Now, we still have 3 electron groups on this particular model, one of which is a lone pair. So I have a double bond that's here, a single bond that's here, so 2 bonding groups. And then there's a lone pair on this oxygen that's right here. Okay? That means that I have three electron groups, 2 of them being bonding, 1 lone pair. So this trigonal planar structure now has only considered the 2 that are down here, and so that's bent. Okay, we still have the lone pair that's sticking up here, but we don't talk about that when we talk about the molecular geometry. So we're talking about that same structure, but only the bent portion of it. And our bond angles are still 120 degrees. This has been squished a little bit because that lone pair takes up a little more space. So it's approximately 120 degrees. Okay, so that's how we go to that. The next one that we talk about is tetrahedral. And that's what that word is, tetrahedral. So if I have 4 electron groups, all of them being bonding, this is a tetrahedral structure. Okay, this is the way that carbon exists almost all the time. All right. Here we're looking at TiCl4. Okay, that structure, Ti, bond to Cl, bond to Cl, bond to Cl, bond to Cl, no lone pairs. So 4 bonding groups. We're going to have a structure that has 3 of these down and 1 up. So in 3-dimensional space, that looks like a tetrahedron. Okay, that's why it's called tetrahedral. And our bond angles are 109.5. That's my bond angle on that. It's easier to see this in the 3-dimensional structures. Much easier to see. Sometimes when we draw this, you'll see it drawn this way as opposed to this way. And again, we have this dashed line that means it's going back into the page, and this wedged line that means it's coming out of the page towards you. So that's what we're talking about there. So that's my tetrahedral structure. Now, that's if all of them are bonding groups. If one of those is a non-bonding group, like on an H3 where I have a lone pair up here, then we're going to be talking about a slightly different molecular geometry, and that's called trigonal pyramidal, because it's not flat, it's still tented, okay? And so it's trigonal pyramidal, right? And that lone pair is sticking up here by itself. Now, all of these bonds then slide in a little bit, slightly less than 109, and that's okay. You don't really need to know that. Approximately 109.5 is fine, but that's called trigonal pyramidal. So I went from the tetrahedral electron geometry to my molecular geometry of trigonal pyramidal because of the presence of 1 lone pair. Okay. When we look at a tetrahedral structure that has 2 lone pairs, you're familiar with one of these. That would be H2O. So my hydrogen is bound to my oxygen. My oxygen is bound to another hydrogen. That oxygen has 2 lone pairs on it. So those 4 electron groups still exist in that tetrahedral structure, but 2 of them are non-bonding groups. So when I talk about the bonding, it's bent. Okay, all I can see is this part. And that's why you see water drawn the way it's drawn. Okay, that's because its molecular geometry means that it's bent. Okay, and you'll see that we still have additional squishing of that one bond that's left, the HOH bond. And that's because of the presence of the lone pairs, so that takes a little space. So there you go. So we went from tetrahedral, 4 bonding pairs, to 2 bonding pairs to lone pairs. That means we go from our electron geometry of tetrahedral to a molecular geometry of bent. Okay? The next one we're going to talk about is 5 groups. So when we talk about 5 groups, that's going to be an electron pair geometry of trigonal biparameter. So in the plane, we have 3 of them, 1 up and 1 down. That's trigonal biparameter, and it's biparameter because it's up and down. So 5 of them, all of them being bonding. PF5 is one of these. Okay. In 3 dimensions, we see that this one is going back, this one is coming towards us, this one is in the plane. These 2 are also in the plane. We have approximately 90-degree angles between the up and the plane, and 120 degrees in the plane. Okay, so those are the ones that we're talking about. And that's what this looks like when everything is a bonding group. It's called trigonal biparameter. Spelling does not count, so don't worry about that. When we take one of those groups and turn it into a lone pair, we're now talking about 5 electron groups in total, but 4 of them being bonding. So we've got a lone pair that's stuck off here. SF4 is one of these. That means that one lone pair is in the equatorial plane, and then everything that's left, these 4, if you think about it, if you turn this on its side, it actually looks kind of like a seesaw, right? And so that's why it's called a seesaw. So I can imagine that this thing has 2 legs that are sticking down and playing across it. That's the seesaw. So 5 electron groups, trigonal biparameter for the electron geometry. My molecular geometry is then called seesaw, and that's because it has 4 bonding groups and 1 lone pair. Okay? Now, if I take my trigonal biparameter electron geometry and I replace that with 2 lone pairs, so that I have, just like we talked about with that CLF3, so I've got the 2 lone pairs. We have approximate bond angles of approximately 90 degrees. Everything comes back to approximately 90 degrees at that point. And we talked about the fact that this, instead of being that trigonal biparameter electron geometry, appears to be T-shaped, because we have those 3 that we can look at. So that's a T-shape. Okay. Our next structure is if we take that base of 5, so that trigonal biparameter, but we've taken and replaced a bunch of those lone pairs with, or the bonding pairs with lone pairs. And now we have 3 lone pairs. If that's true, all of the equatorials become lone pairs, and we're left with the up and the down on the XE, so up and down there, and that's a linear structure, 180 degrees between them. Okay, so 2 bonding groups, 3 lone pairs. This is going to be linear in molecular geometry. Its electron geometry is still trigonal biparameter. Okay, we can get to linear from a couple of different places, so you may need to pay attention to what is that electron geometry. In all likelihood, you will get the question, what is the electron geometry? What is the molecular geometry? To see if you understand the difference between them. Okay? And that usually means that they're not all bonding groups, so that I can tell if you can tell the difference. That takes us out of our 5 electron groups and brings us into our 6. So if we have 6 electron groups around this thing, I have 4 that exist in the plane, 1 up and 1 down. That's considered an octahedron, right? That's that structure there. It's octahedral. Since there are no lone pairs on this one, its molecular geometry is also octahedral, and it has 90-degree angles for this. So SF6 is one of these. Now, SF6 is a violation of the octet rule. It's more than 8 electrons around that center, but it does still exist. Okay, so there's that. Now, if I replace one of those bonding pairs with a lone pair, so here I have 1, 2, 3, 4, 5. Okay, and I've got that lone pair that's on there. All right. What we have here, 6 electron groups, 5 bonding groups, and 1 lone pair. Going from octahedral, this then becomes square parameter. Okay. So we have the 4 in the plane and 1 up. So square on the bottom, parameter, because there's the 1 up. So that lone pair ends up on the bottom. I will not ask you where that ends up. It's just FYI. Sometimes you get asked. I'm not going to ask. Okay. The next one that we talk about, we still have our electron geometry as octahedral, so 6 as our base. But now we have 4 bonding groups and 2 lone pairs. When we do that, we have our lone pairs up and down. That means that we have our 4 that are left are all in this plane. Okay. Now, on paper, it's very easy to see that this looks like a tetrahedron, but it's not. It's absolutely not. So we call this square planar. Okay. So sometimes the drawings that we have on 2-dimensional paper don't really represent that 3-dimensional structure. This is part of the problem that we have, is how do we do that? And that's where those dashed lines and wedged lines come in, trying to make that look more appropriate. Okay. So approximate bond angle is 90 degrees, and that's for 4 bonding groups, 2 lone pairs, with our base as 6 electron groups. So octahedral split plane. Okay. That's all of the structures that we're going to talk about. So while there are, in theory, other structures that exist, those are the only ones that we see practically. Okay? So those are the only ones that you're going to find on this table. So your job is to figure out how many of them are bonds and how many of them are not bonds, so lone pairs. Once you can identify that, then you can tell me what's the geometry of the electron groups, i.e. that electron group geometry at EG, and what is the molecular geometry, the MG. And if I ask you what the bond angles are, they're right there. Okay. Now you may get asked, what's the example of this? You can pick whatever's on the chart. That's perfectly fine. That doesn't matter. You may find that some of the things you get asked about are actually on this chart. So use your resources as they're available. So if I ask you about SF4, you'll know what it is because it's right here. Okay. So make sure that you're paying attention to the fact that you have some of that information available to you. It may mean that you don't have to do quite as much work. Okay. Now, as I've mentioned, no work equals no credit. If I don't see work, I can assume that you Googled something. Right. Now, if you pulled it off of this table, then you should have enough information to be able to draw me a base structure. Okay. So you need to be able to do that. That's why no work, no credit. I need to be able to see the logic that got you to where you are. And it's more about the logic than anything else. So I need to understand your logic, because if there's a failure in your logic, we need to correct that. The other thing is that if the logic is fine, but something happened along the way, like your calculator hates you like it does to me, then that's not a big deal. Okay? Calculators mess up. We get an opportunity to go back and look at those things again if we're not taking a test. Right? So that's not as much of an issue as not understanding what we're talking about to begin with. Okay? So that's where we are with that. So again, working through drawing our Lewis structures, then assigning your electron geometry and molecular geometry and bond angles from this table. I would do all of your practice using the table. Again, if you want this exact copy, I will provide it to you. It's slightly different than the one that's presented in the lecture notes, but not much. Okay. So that would be my recommendation as far as that goes. Are there any questions on the non-math stuff, Lewis structures, Vesper, any of that before we start talking about the text? Okay, I'm going to pull this out of the way. Hold on, sorry. Thought I had this set up here. I don't. Give me 2 seconds. So what we're looking at here, this is a preview of the exam. I have the ability to do this so that we can look at what was in this. This is going to be presented to you the same way that you would have seen it as a student, so that we can talk about what's going on with this test. Okay. Let me grab some scratch paper so that I can actually talk about this. Okay, so just in case I need to scratch. Provide an example of a named part of the periodic table. Be sure to provide the symbol. I was looking for the symbol here. So it says alkaline earth metal. So if I look at my periodic table, and I want to look at my alkaline earth metals, I know it's one of the metals, right? And so I'm going to turn off my work too. It's one of the metals. We have a couple of groups in the metals that we were supposed to know. One is the alkaline metals, one is the alkaline earths. So this group right here, group 2, these are the alkaline earths. Anything in that column would have been acceptable. When we talk about noble gases, that is 18, sorry. So our noble gases are over here, the helium, neon, that structure that we're all trying to become is that noble gases. Okay, so anything in that group would have been okay. And when I said period 3, that is row 3. So period refers to the row. So anything in this row would have been acceptable as an answer for that. Questions about that? If you guys do have questions, feel free to interrupt me, no problem at all. We talk about manganese 2 sulfates. Closed it. So manganese is this guy right here. So he's Mn. That's his symbol. That 2 after the name indicates the charge on that ion. Sorry, technology is not working with me today. Skincare. Thank you. Pulling over my paper. I'm looking at manganese 2 sulfate. Again, manganese is Mn. I know that that 2 refers to his charge because since he's a D block metal, I don't know what his charge is. So that 2 indicates his charge. So he's a 2 plus. Sulfate is one of those polyatomic ions that's listed on the exam handouts. That's an SO4 2 minus. Since I have Mn2 plus and SO4 2 minus, the way that I would do this is Mn charge on sulfur or on the sulfate becomes the subscript there. SO4 charge on the manganese becomes the subscript there, but I can divide that to give me MnSO4. Since they're the same number, I don't necessarily need to put the 2's down there. Okay. But that's technically what I'm doing. So whatever the charge is on the Mn, that becomes a subscript down here. Whatever the charge is on the SO4 2 minus, that becomes a subscript down here. The only reason I don't need it here is because they're both the same. So that's my MnSO4. So this is the answer I was looking for there. Correct formula for boron trifluoride. Well, boron is B. Obviously, all of those say B. Trifluoride means 3 fluorines. Okay, so I'm looking at 3 fluorines. So that's BF3. I don't see that, which is true. So this is none of the above because none of those are the correct formula for boron trifluoride. I know that's a little bit mean, but that is the way that that one was set up. Select the correct formula for sulfur diiodide. Sulfur is S, iodide is I, and it's diiodide, so it's Si2. That's this one right here. Correct formula for barium carbonate. Now, barium is Ba, carbonate is CO3 2 minus. Again, that's one of those polyatomic ions that's in the exam handout, so I'm supposed to know. Now, Ba being where he is, which is right there. He's now calling earth metal, so he's a 2+ as well. So again, I would put that together to be a BaCO3. So same charge, so I can have that BaCO3, which is this one. Correct formula for gold 1 oxide. Okay. Gold is Au. He's here in the middle. He's right there. That's gold. So he's Au. He's listed as gold 1. That means his charge is +1. He's with oxygen, who's an O2 minus. So to make that work, I have the Au with the subscript that is the charge from O, and O with the subscript that is the charge from Au, which is an implied 1. So this 2 becomes the subscript here, and the 1 becomes the subscript there. So Au2O is what we're looking for there. That's this one right here. When we name compounds, ZRO. Now, when I'm naming a compound, I need to know where it is. I absolutely need to know where it is, because the rules for nomenclature depend on where that thing is. So if I find my ZR, ZR is right here. So he's a metal. Okay. Oxygen, non-metal. So that's a metal to non-metal bond. That's ionic. Okay. If it's ionic, then he's going to be zirconium, which is the name of that ZR. It's right here, zirconium. And then it's the oxygen is the last part, but instead of being oxygen, we change it to oxide. That's how we handle oxygen when it's the second part. So normally we take the name, change the end of it to "ide." For oxygen, that becomes oxide. So zirconium oxide. We have no prefixes that indicate how many of them there are, because their charge determines how many there are. For ionic compounds, that's what we do. Okay. We talk about Rb2s. Rb is a metal, S is a nonmetal, so the same rules apply. So Rb is rubidium, and oxygen again, that's the oxide. So rubidium oxide. When we talk about N2O5, nitrogen is a nonmetal, oxygen is a nonmetal. So here we need prefixes. So because it can be N2O5 or NO2 or any number of those combinations, I need to know how many of each exist. That is absolutely necessary. And so when we have N2, that's a dinitrogen. And then O5 is a pentaoxide. And pentaoxide is technically the way that that's spelled. Sometimes we leave off the A. Either one's okay. So that's the name on that. Cool, that's fun. Now this next one, I look at this and I go, right, that's a really big thing there. Now, I only know how to name 2 things, and they're usually for binary components. So metal to non-metal bond or ionic compounds. Ionic compounds can have polyatomic ions on both sides. So I look in my list and I see that NH4 plus is a polyatomic ion. And PO4 3 minus is a polyatomic ion. So this is an ionic compound. Therefore, I just need the name of those 2 ions. So NH4 is ammonium. And it's ammonium because of that H4 plus. And then phosphate is PO4. So that's ammonium phosphate. And again, the number that's present for both of those is determined by that charge. So I don't need any prefixes for that. Now, when we talk about CCl4, for CCl4, I have carbon and I have chlorine. Both of those are non-metals. So I'm looking at different rules there. When I look at those different rules for carbon and chlorine, I know I'm going to need the name of the carbon. There's one of them, so I don't need to put the mono in front of the carbon. I can put it. So I could put monocarbon, and then tetra is 4. Tetrachloride. Or I can just do that as carbon tetrachloride. So again, because it's a non-metal, I need those prefixes out in front. Questions about that? Most people got this one. So my neutron is a neutral subatomic particle, so that's 6. Isotopes are 2 elements with different numbers of neutrons, that's 2. Oxygen, O, is an element that has an atomic mass of 16, that's 5. An electron is a negatively charged subatomic particle, so that's 1. The d orbitals are the ones here in the middle. So if I want to look at my d block, I can call that up here. That's this block right here in the middle. I know that there are 10 of those. There are actually 5 of those. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I find the one that says orbital type that can contain 10 electrons total, and that's 4. When we talk about a proton, that is a positively charged subatomic particle, and that's 10. S, my S block, is over here, and there are 2 electrons that can exist in that S block. So orbital type that can contain 2 electrons is 8. Sulfur, S, is an element that has an atomic mass of 32.07, so that's 7. When we talk about P, my P block is over here. 2, 4, 6 present there. So I'm going to find the one that says 6, which is number 3. And when we talk about F, F is that group down here. And if I count all the way across this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And of course, that's the last one that says contains some things in it. So that's not. Okay. So that's everything on that. Now, a Bohr representation of boron in your scratch paper, and be sure to upload that to the assignment box. Be sure to label all particles. Here, please indicate the number of protons, neutrons, and electrons in 10B. So when we talk about B, turn my F off. B is right here. So I know that boron is atomic number 5. So boron is number 5. This out of the way. If he's number 5, then he has 5 protons. Since it's a neutral compound, I need 5 electrons. They have to be equal for it to be neutral. And if we want to talk about the number of neutrons that are in this, the neutrons is equal to the mass number, which is this 10. So it's this number up at the top, the mass number, which is 10, minus the number of protons, which is 5, which is 5. So that's how we do that. And of course, my neutrons and protons go in the middle. Stupid ways, but that's okay. And then as long as there were 5 electrons out here, that's all I cared about. They don't necessarily need to be in the correct places or anything else. I would have done them like this. Because I have my 1s, my 2s, and my 2p, but that's just for me. That is not required for you. Cool, that's fun. When we talk about 10, 10 says, I bought a new computer with a petabyte drive. So when I look at petabyte, if I'm looking on my exam handouts, I see that peta is listed as 10 to the 15th. So this is a 1 times 10 to the 15th byte, because it does have how many bytes that is. So I need to do that. On question 11, I have a .357 caliber bullet that measures 200 grams. What is the mass of this material in ounces? Well, I see that I have 200 grams. And I also see, and I'm going to move this down here again, 200 grains. I also see that 1 grain equals 0.00229 ounces. I want to know the mass in ounces, so I'm going to take that 200 grains, and I'm going to multiply that by 0.00229 ounces per grain, because that's what that looks like. The grains will cancel. That'll give me an answer that's in ounces. And I think numbers, so 0.229, and then give me 0.458, which is great because I only have 3 sig figs anyway. So 0.458 is what I was looking for. Many chemistry conferences have held a 50 trillion angstrom run. How long is this run in kilometers, and how long is this run in miles? And you see that 1 angstrom is 1 times 10 to the minus 10th meters. Okay, so the first thing I need, I know it's 50, and I know it's trillion. So if I look at my exam handouts, if I look in here, I see that trillion is associated with tera, which is 10 to the 12th. So that means I have 50 times 10 to the 12th angstroms. And I just write that as angstrom. I know that 1 angstrom is 1 times 10 to the minus 10th meters. And I asked for this in kilometers and miles. First, I'm going to go kilometers. If I'm in meters, I have 1,000 meters per kilometer. And that's the calculation I need to do there. And if I'm pretty sure that if I do that, 50 times 12 times 1, 10, negative 10, divided by 1,000, that should be 5. So that's 5 kilometers. Hey, that was exciting. Now, if it's 5 kilometers, I can set that calculation up again and then use one of the conversion factors from my exam handout. I can see from here that 1 mile is 1.61 kilometers, or 1 kilometer, to 1 kilometer equals 0.6214 miles, or I can use 1 mile equals 1.61 kilometers. Either one of those is fine. Now I know that I ended up with 5 kilometers. So me, I like to do it this way. 1 mile is 1.61 kilometers. Because I like to work with the numbers that are greater than 1, so that's why I do that way. So I take my 5 and I divide that by 1.61, and that gives me 3.1. And technically this should round to 3 because this right here is only 1 significant digit. There's no period, so it's only 1 sig fig. So this should be reported as 3 miles. That's not exact, and that's fine, but that's how that looks. So there's that. I have a coolant system that's designed to hold a 10-gallon keg. When I go to buy I should say keg, at a local ABC store, the measurements are only given in liters. What volume in liters should I get from my coolant system? So there are a couple ways I can do this. So I'm looking, 10 gallons is what I have. I need to get to liters. Now, I have some information that's been given to me. I've been told that 1 gallon is 128 ounces. I also know that 28.35 milliliters equals 1 ounce. Okay, so I can go from gallons to ounces and from ounces to milliliters, which I can then use to get to liters. So that's one way. I can set this up to go 10 gallons. 1 gallon, 128 ounces. 1 ounce is 28.35 milliliters. And of course, there are 1,000 milliliters a liter. So that calculation will work. One of the other things that I can look at on my on my exam handouts, I think I saw that 1 gallon equals 3.785 liters. So I can also use that one. So 10 gallons. 3.7. Actually, this needs to be on top. 3.7854 liters per gallon. Okay, let's cancel there. And either one of those will leave me with an answer in liters. 10 times 128. This one gives me 36.2. And if I take and multiply the 10 times the 3.7854, that gives me 37. They're not exactly the same. It happens. Depends on where you take those sources from, what you end up. Okay. Now, again, since this number technically only has one sig fig, what I was looking for was a reporting report. But I didn't choose this one as the one that I looked at for sig figs, so that's what we're talking about. So any issues with that? Now, when we talk about our periodic trends, and we are looking at something like ionization energy, I know that ionization energy increases as we go across the table and up, increasing ionization energy. And so if that is the case, and I look at my table, because that's what it's, and I compare gallium and beryllium, I have Br over here, and gallium is right here. So gallium is therefore smaller than beryllium. So in terms of increasing, it's going to be gallium 1, beryllium 2. When we talk about increasing atomic radius, and when we talk about atomic radius is one that's a little bit weird. Remember that as we go across a group, it gets smaller. So while it gets bigger going down, it actually gets bigger going that way. And that's because we have more positive charge in the middle, so it pulls in more. So it's a bigger effective nuclear charge. So if I'm looking at bismuth, astatine, beryllium, and polonium, so bismuth, astatine, polonium, and tellurium. So I know that astatine is smaller than polonium, is smaller than bismuth, right? Look at increasing atomic radius. So astatine smaller than polonium, smaller than bismuth. But I also know that Te is above that. So Te is going to be the one at that. It's the smallest. Okay. So that's how we do that. Increasing, decreasing ionization energy. Oh, that's the opposite terms of what we talked about before. So this is the other way. So if I want to go from decreasing, the bigger one is going to be Br. And then that. So we reverse the order on those two. Okay. All right. Question 17. Which of the following are correct representations of the electron configuration for I? Okay. So where's my I? Well, I is right here. He's one of these ones way down here. He's in the 5th row. He's over here is a noble gas, or next to noble gases. He's a halogen. So if he's in the 5th row, I know that everything from row 4 is included. So if we're talking about getting to row 4, row 1 is a 1s2. Row 2 is a 2s2. So again, row 1 I have 1s2. Row 2 I have 2s2, 2p6. Row 3 I have 3s2, 3p6. We get to row 4. We're now talking 4s2, 3d10. Remember, d is n minus 1. So 4s2, 3d10, 4p6. And then we're going to row 5. Again, we're looking 5s2, 4d10, and then 4p5. 5s2, 4d10, 5p5. Okay, so that's my total electron configuration that I would write if I was writing out the whole thing. Now, do I write out the whole thing? That depends. There's some other ways that I could do this. The nearest noble gas configuration we could talk about technically would be the Kr is the noble gas before it. And then beyond that, I have that 5s2, 4d10, 5p5. This can also be written, depending on who you're asking, as Kr 5s2, 5p5, because some people think that since it's a 4, it should be included with the krypton, even though that really doesn't happen. So whatever. That is one of the ways that we can talk about that. Okay. So this is correct. This one is not. That would be I minus. And while I minus is the normal ion for that, we did not ask about I minus. So that one is not correct. We never talk about it being Xe, because even though Xe is the closest noble gas, it's this one right here, that it would become if it wasn't. That is not the correct electron configuration for I. That would be for I minus. So it's not that one. It's certainly not Xe minus 1 4p, because that actually doesn't exist. We don't do an electron configuration where we subtract things out. We only do things where we add them in. So this one is not right either. Now looking at these next two, I look at that and go, okay, neither one of them is normal, but that doesn't necessarily mean anything. And so I asked myself, do either of these make sense in terms of what we're talking about? Now argon is in row 3. So if we're talking about argon's core, and then what's beyond that, that's going to be a 4s2, the 3d10, and then the 4p6, and then my 5s2, the 4d10, is my 5, and then it's a 5p5, not a 4p4. This is incorrect. So this one and this one are both correct. Technically, both of those should have been selected, but if you got one of them, that was fine. So those are the two that I was looking at. Okay, and here's the one that people hate me for. So, given the electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Right, so I'm in row 4. And I have my 1s2, 2s2, 2p6, 3s2, 3p6. Those are the ones that are here. I have my 4s1, 3d5. Well, that means that next row contains 6 electrons, correct? So beyond that 3, I have 6 electrons that I need to put in. So normally I would go 1, 2, 3, 4, 5, 6, and that's chromium. It absolutely is. Now, what happens when we get to chromium? Chromium is one of those groups where we have weird exceptions, right? So these guys right here, because they're in a 4, or in the D, 1, 2, 3, 4, 4 right there, they're almost half full. And so what typically happens is instead of having that 4s completely filled as 4s2 3d4, we move and have 4s1 3d5. This is one of those exceptions. So that's what we're looking at for that. So this is chromium. And that chromium is based on the fact that the total number that I'm looking at of electrons, if I add all of those up, is 24. So if there are 24 electrons, I have an atom. It's not an ion, so I know it's not charged. Okay? So if it's number 24, he has 24 protons, 24 electrons, and that makes him chromium. So 24 is here. Chromium, 8 bars, go there. How many protons should it have? 24. Can it lose an electron? And the answer is yes. Anything can lose an electron if you add enough energy. What would be the charge on this ion when it loses an electron? Positive. If it loses 1 electron, it's +1, positive, just to indicate that you've taken away a negative charge. So it's positive. What would the electron configuration be if it lost an electron? Well, because this is a weird one, right? It's weird in the way it's set up. This would end up being 1s2, 2s2, 2p6, 3s2, 3p6. And then we get into that 4s1, 3d5. It always takes it from the one with the highest principal quantum number. So the highest number out in front. So it comes out of that 4s and it leaves a 3d. Okay? So it removes that 4s electron. That's technically what it does. As long as I got an electron configuration that showed 1 less electron, that's what I was looking for. But this is the technically correct answer. All right. On question 19, I'm reacting 32.67 grams of silver with 64.35 grams gaseous fluorine to make silver 2 fluorine solid. Write the balanced chemical equation for this process. All right. So my silver, if I look at silver, silver is here. He's Ag. He's one of those guys in the middle, so I don't know what his charge is going to be. I'm reacting him with gaseous fluorine, F, is one of those ones that's always diatomic. So my diatomics, again, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. So F exists as F2 gas. Okay. And that gives me silver 2 fluoride. So silver 2 is Ag2 plus. Fluoride, F minus, again, picks up 1 electron to become like neon. I know it's 2 plus because it's silver 2. Okay. When I put those two together, see what I'm drawing. When I put those two together, the charge on this becomes a subscript on this. So I have an Ag, which is a 1 because there's a 1 there. And then F is a 2 because of that. So it's Ag2F. So that's what we were looking for, what I was looking for there. And of course, this is also a solid. So from a technical standpoint, that's what I mean. So that's what I was looking for. So what's the ratio of fluorine to silver? When I ask ratios, we're talking fluorine to silver. We're talking about in the balanced equation. And that's a 1-to-1 in the equation as I've written it. Now, understand that when I grade these things, if you got the first one wrong, that's okay. I mean, you get points taken off for the fact that you got it wrong. But I'm not going to penalize you if you answer the rest of the questions based on what you already wrote. So you may see answers that I have given you credit for that are different than this because they were based on what you put as the balance equation. What's the ratio of silver to silver 2 fluoride? So then I'm looking at the Ag to the Ag2F. That again, in this equation is 1-to-1. Okay. What is the number of moles of silver present here? Well, that's based on that 32.67 grams of silver. So 32.67 grams of Ag. I also have 64.35 grams of F2. Now, if I want to convert that to moles, I need to divide by the molecular weight of the Ag. So if I pull over a periodic table and look at what is that mass for Ag, you'll see the Ag right here is 107.868 on this table. I don't think it had that many decimal places on it. So that's what I'm going to divide by. That is grams of Ag for a mole of Ag. If I do that math, 32.67 divided by 7.68 is the 0.30. I have 4 sig figs there. 0.29 moles of Ag. So 4 sig figs is my answer because I start with 4 sig figs right here. This one is considered infinite, so I need to look at how many are. Okay, I need to do the same thing. I need to look at what is the number of moles of fluorine gas. I take my mass of fluorine, it's 64.35 grams, and that's a fluorine, which is F2. And 1 mole of F2 is not 18.9 or 998, which is, I believe, was on the test. It's twice that. So this mass that I'm looking for here is 996. So this formula determines what that mass is. So it's F2, so it should be 37.996 grams. As long as your division was done, if you said it was F, and you divide by the mass of F, that's fine. Now what you don't do here, and what I saw a couple of times, was if somebody had balanced those so that there was a 2 out in front of those, and it was 2F2, you do not multiply this by 4. We never multiply by the number that's out in front of it when we do this calculation. That is something we would do later if that ratio needs to be taken into account. So I'll do that. 64.35, 77.6. I do 1.694 moles of F2. Again, that's 4 sig figs because of the number that I started with. Okay. How many silver atoms are present here? Well, if I know the number of moles of silver, then I can take the number of moles of silver and multiply that by Avogadro's number. Because that is in atoms per mole, or molecules per mole, particles per mole. Okay. So I can take that 0.3029 times 6.022 to the 23rd, and that gave me 1.824 times 10 to the 23rd. So 1.824 times 10 to the 23rd. That was how I was looking for you to put that in there. How many molecules of fluorine are present? We go through this similar calculation. So I have 1.694 moles of F2. Same number, 6.022 times 10 to the 23rd molecules of F2 per mole of F2. It's 1.020 times 10 to the 24th. What's the charge on fluorine? -1, -1, either one of those is fine. What's the percent composition of each element in the product? Okay, so my product, again, I report as AgF2. 2, not AG2F. AGF2. That's what I wrote as my product in my balanced equation. So AG2F. What the heck did I do? I wrote it wrong there. Please. Wrote it right here, but not there. There. All right. So AGF2. So that is what I need to know the total mass for. So if I do that, that's that 107.8 something. 868. 868. I'm going to add 2 times the 18.998. That gives me a total of 145.864. And that's grams per mole. That's the total mass. If I want a percent composition, I need to look at the mass of each component. So percent Ag is going to be equal to the mass of Ag. There's 1 Ag, so it's 107.868 grams per mole, divided by the total mass, 145.864 grams per mole times 100. My percent F is going to be equal to the 2 times 18.998, and again that's grams per mole, divided by the 145.864 grams per mole, and that has to be multiplied by 100 as well. And if I do that happy math, 107.868 divided by that answer times 100. 73, and I reported this as, I reported it as 4 sig figs, because why not? Technically it should be more than that, but that's okay. Just go with it. So that's 73.95 that I had there. Alex asked you to round up, and I asked you to report the cation before the anion, so that means the metal before the non-metal. So that's why the 73 goes first. And my F is going to be 2 times that 18.98 divided by 10.864. And this is 26.5. Now, Alex asked you to report this in the nearest decimal place. So if the figs were not, quote unquote, appropriate, I didn't worry about it here. Technically, this would be limited by the number of significant digits in the mass of each material. So you see 6 here, I see 5 there. So I would report this one is 5, this one is 6, if I were doing it correctly, but I'm not. Okay, so those are the numbers that I was looking for there. Okay. So hopefully that's okay. Now, when we talk about our bonus, a couple of bonus questions that we dealt with, we want to balance the following equation. So I want to know what this particle is. I have a 0, -1 E goes to 142.56 BA plus 3 times 10 N plus 1936 KR. I need to look at the top numbers. So 142 plus 3, because there are 3 of them, plus 19 is the total on the top on that side, on the plus. So 142 plus 3 plus 19 is 164. Now 164 is going to be the same on the other side, but it's going to be something plus 0 equals 164. So that something is going to be the 164 because there's no contribution from the 0 that's here for the electron. Right, and we do the bottom numbers. We have 56 plus 3 times 0 plus 36. So 56 plus 36, that gives me 92. And of course, that 92, to get rid of this contribution right here, typically what I do is I take 92 minus whatever this number is. And that's minus a -1. and that gives me negative, or gives me 93. So that number has to go up to be able to compensate. So 93. And that's what I was looking for, was how do you deal with this number here? If I look on the table, I see that 93, if I'm not mistaken, is NP. Yes, 93 is on. So that's NP right there. So again, find the sum of my top numbers and then subtract the contribution I already have. So that would be the 164. And then sum of the bottom numbers and subtract the contribution of what I already have, which is the -1. So that gives me 93. Based on the 93, I know that's NP. So that's how I get to that answer. Material has a percent composition of 20.19% Mg, 26.64% S, and 53.17% O. What's the elemental formula of this compound? So again, the way that we handle this is to find the smallest whole number ratio between those components for that elemental formula. We do that by assuming that this percentage is the mass out of 100 grams. By 20.19 grams of Mg, 26.64 grams of S, and 53.17 grams of O. Now we need to make a molar ratio for each of those. So I take 20.19 grams of Mg, I divide that by the molecular weight of Mg, which on my table here is 24.305. And again, these numbers might be slightly different than the sig figs you had on the test. I would set up the same calculation for the 26.64 grams of S. I will divide that by the molecular weight of S. Here, 32.06. And I will set up a calculation for that 53.17 grams of O, and 1 mole of O is 15.999. That would give me a number of moles for each of these. So 20.19 divided by 24.305. 0. Now this should be 4 sig figs. 8307. So 0.8309. 53.17 divided by 15.9 gives me 3.323 mole of. Now, in theory, what I would then see is that it's Mg 0.8307 as 0.8307 and O 3.323. But we don't report anything that looks like that. And so what we need to do is make this the nearest whole number ratio. So we're going to divide by the smallest number. Now, in theory, this is not, in theory, I would divide by the 0.8307. Okay. What I'm actually going to do is divide this by 0.830. Because that's really close to both of them. And I'm going to end up with a slight, issue from the rounding, but it's all going to go away in the end. So I'm just going to do it that way. That leaves me with an Mg1, S1. And if I do that 3.323 divided by the 0.830, that gives me 4. And of course, if I leave off the ones, that's an Mg. So that's the element formula that I'm looking for that. I need to produce an ionic compound to use, and I only have a chalcogen and an alkali metal to do this. With one chalcogen and one alkali metal. And show me the balanced chemical equation to form an ionic compound for these two elements. Be sure to label each element as chalcogen or alkali metal. Okay. So I need a chalcogen and an alkali metal. And I know that I want to make an ionic compound, so I need to know what their charges are. Now, my alkali metals are this group right here. So that group. Notice when we do this coloration, that H is not included. H is not considered a metal, it's considered a non-metal. So even though it technically exists in this group, it is not considered an alkali metal. So any of these metals would be fine. I happen to choose lithium as my alkali metal. He's Li, and of course he's going to be an Li plus when we're looking to make that ratio for him. Yeah, so I didn't need to do that. I need to do something else. Those, no, not that one. Those are my halogens. Those are my chalcogens. 16 is called the chalcogens or oxygen chain. So my chalcogens is anything in that group. Now, I chose to use, you can use S. I'm going to use S at this point just because it makes my life easier. So sulfur, it's S, use an S2 minus. Okay? Now, the reason that I chose S and not O is because O exists as a dimer, so it would be a little more complicated to balance that equation. I know how to do it, but it's perfectly okay. So I have my alkali metal is lithium, my chalcogen is sulfur. I know that lithium is +1, S is -2. So when I write that equation, it's going to be Li solid plus S solid. And I don't need to include the states, but I have that. And then I'm going to have Li, and I need the subscript to be the same as this charge, 2S. And so I need to have 2 Li's out in front of this to make that work. That was the purpose in asking you to do this, is because one of these is a +1, the other one is a -2. So let's make sure that we get our formulas correct and then can balance that equation. Now, had I chosen to do Li plus O2, Li to O, and of course I need 2 of those to get the 2 oxygens, and then I need 4 of those to make that balance. But again, not a big deal. It's just something that we need to be able to do. Okay? So that's that. And then we get to 23. And 23 is a bit of a bear, just because there's a lot to pull out of this question. So it says, toxicologists use the term LD50 to describe the number of grams of a substance per kilogram of body weight that is a lethal dose for 50% of test animals. Calculate the number of arsenic-3 oxide molecules corresponding to an LD50 value of 0.0146 for a 179-pound man, assuming that the test animals and humans have the same LD50. Provide your answer in scientific notation with the correct number of significant digits, and on your scratch paper, indicate the formula of arsenic-3 oxide. That's a lot of information. One of the things that they asked me to do is provide the formula for arsenic-3 oxide. If I want to do that, I need to look at my periodic table, because I got to find arsenic. So arsenic is right here. He's AS. I know that he's arsenic-3. And if he's 3, that means he's a 3+. Now, oxide, again, O, he's a -2. I also have oxygen, O, which is -2. Okay, so those are the 2 components that I need to put together to make arsenic-3 oxide. Now, what happens here? I have AS, and the subscript is the charge on the oxygen, so that's a 2. I have O, and the subscript on the oxygen is the charge on the arsenic, which is 3. As2O3 is the formula for arsenic oxide. And it's arsenic-3 oxide. All right, I got that part. Now, I need to calculate the number of those that correspond to an LD50 value of 0.0146 for 179-pound man, assuming the test animals are the same. Okay, now, when I look at this 0.0146, this is grams of AS2O3, because it's grams of substance per kilogram of body weight. Okay, so those are the units that go with that number. All right, fine. I need to get to number of molecules, so that means I need to get to moles. In and out, convert to moles. And I need to take into account this right here. So 0.0146 grams of AS2O3 are required per kilogram. I know that this is a 179-pound person. So I have to convert that to kilograms. And I can do that with information that I found on an exam handbook. I can see that 1 kilogram is equal to 2.2046 pounds. Okay? So I can take my 179 pounds, I can multiply that by 1 kilogram and divide by the 2.2096 pounds. That cancels my kilogram, my pounds, and leaves me kilograms. So 179 divided by that 2.2096. And that means that this is 81.0 kilograms. Okay, so that'll tell me how many grams of AS2O3 are required to kill this person. 0.0146 times 81. That's 1.1826 grams of AS2O3 that are required to kill this person. Awesome. Now, I need to get to moles. So if I have a mass, I can divide by the molecular weight of AS2O3. In order to do that, I need to know what the mass of the AS is. So if I come over here, I see that the mass of AS 74.922, and of course oxygen is 15.999. So if I have 2 AS, 74.999, no, that's not 22, sorry. 22 times 2 plus 3 times 15.999 gives me a total mass of 197.841 grams of AS2O3 per mole of AS2O3. So that'll get me to moles. Awesome. That's moles. I love it. Now, is that my answer? No, because what I got asked about, the number of those molecules, right? And so I know that if I go from moles to get to number of molecules, I need to multiply by Avogadro's number. So 6.022 times 7/23 molecules per mole. And so that's the calculation that I need to do. 1.1826 divided by 197.841 times 6.022.3. And that gives me 3.59. 3 sig figs there. So 360. Is that fine? Times 7/21. And that's molecules. AS2O3. That is required to do this. So that's what I reported here. So that's what I was looking for there. Okay. So that's how I did everything that I did in terms of the calculations for the test. If you have any questions, anything at all that you want to talk about, please let me know. that's everything I have to talk about today. Like I said, you should have comments and the answers available to you when you review the test. You should be able to see the question and the answer that was supposed to come with it. And I've tried to put comments in about how I got all of these things, all the calculations that I just did. So, yeah, if you have anything at all that you want to talk about, I'm here. I'm available.
Hi, I'm back. Sorry.
No, you're fine. How are you?
I was on here trying to figure out, um, still trying to figure out Alex. And nope, I still can't figure it out.
Okay, which part? Where are you?
Remember I sent you an email about the calculations?
Yes.
Okay. So, see if I can share this. Hmm.
I might have to stop.
No, it's okay. Do you have the email I sent you?
Yes, and I responded to it.
Yes, I did see that and I read it and I was like, I'm gonna keep her up on WebEx while I try to do this, but mm-mm. I didn't mean to log out of the whole thing. Let's see. Why am I? Hmm. Okay. Having some. It's gonna make me do all this over? No way! Oh. It's gonna make me do all of it over where it had you take the piece of paper and put it in the oven.
Probably yes.
I thought it was gonna save all of that I did, but it's gone.
I don't really know. Like sometimes it seems to save it, sometimes it doesn't, and I don't understand why it does and why it doesn't.
Okay, this is so I still have my numbers should still be the same. Just be
Maybe
hope so.
because the volumes may not be the same.
Let's see. Yeah, it saved the mass of the filter paper. So it saved that. So that's still there. Everything else is still there as well. I just have to go back in and reheat that paper over and over and over.
Yes.
So I don't know if it's gonna give me the same mass of 1.03, but I'm
We
gonna
can
do
always hope, but yeah, I can't guarantee it. So
okay. 1 second, I'm gonna do that over and then
that's fine.
okay. Oh, and also, if you look at the lecture quiz, we had the we had NH3 But the
Yes.
quiz asked about chlorine.
Chlorine. It did. Yeah, I changed part of it, didn't change all of it. Mistake.
Okay, I was like, oh, I just put 0.
And that's okay, because I mean, they're all pass fail as long as you took it. It's not.
Okay. And then it wants me to record this. When you were going over the test, I kind of kept like, darn.
And again, one of the tests gets dropped, and there's the other. So automatically that happens. But the other thing is that if you make significant improvements after the first test, and you go into the final with that performance being a lot better, and that does make a difference. Like if I can see that your first test is you had to drop a second test too, like that, then we can take a look at that. So that is something I have done in the past for some people when they have absolutely screwed up on the test. You know, I had one student who just could not do Lewis structures at all, but their performance on the first test was better on the final. So we replaced their first test score with their.
Okay, they had a hard time with the Lewis structures and not
Yep.
the math. Wow.
Yes, we have some people who are very mathematic who have a very difficult time with the Lewis structures. I struggled with them the most.
Really? It's the math.
I'm
I mean, I guess because
not
the
a
math
visual
is
person, so
okay.
if there wasn't a formula, it didn't help me.
I guess
So I
that
could
would make
calculate a formal charge, but I couldn't put the electrons where they were supposed to go. So
I guess that makes sense because um with a formula you just plug stuff in, so that makes sense.
yeah,
I'm so
I'm very good at. Okay, that goes with this, and that goes with this. I mean, if it wasn't for units, I would have failed physics. I absolutely know that.
slow. I
I
haven't even
just knew what
gotten
units went with, this is a mass, it has to be this unit kind of
to
thing. So
I haven't even gotten to all of that stuff yet. I'm so stuffy. I'm sorry. I think I should have slept with my fans on.
oh no.
It was so warm in here. It's getting warm outside.
Yes, yes it is.
So okay, it did it did give me the same numbers. Now how can I share this with my mix? Where's my hmm, I don't know, it's not oh there it is. Okay. It will be in Chrome. Which tab is it? Is it this one? Yes.
Yes.
Okay. So I got 1.03 again. So it needs 9 and 10. So I saw your email and you gave me the equation.
Yes.
It had this here too,
Right.
but and I tried to use this and I still was like, these numbers don't seem right. And
Okay.
I guess because I did my limiting reagent as the same thing that they did.
Well, okay. So they have their limiting reagent as CaCl2. And based on the numbers you have, that's not true.
Okay, mine would be calcium chloride.
No. So
No.
yours is sodium carbonate, that first one. And the reason I say that is because they're both the same concentration.
Mm-hmm.
But if I multiply the volume times the concentration, that tells me how many moles I have.
Mm-hmm.
Smaller volume means it's a smaller number of moles. So since I have a smaller volume of sodium carbonate than I do of calcium chloride,
Mm.
that's my limiting reagent.
Okay. So where's so I did all this math and I was like, these numbers just don't seem right. So I was like, I'm gonna just ask her about it tomorrow. Oh, here it is. So I did 96, I did 96 milliliters
Yep.
of NaCO3, and then
Yep.
I did my unit conversions, and I
Right.
would have put 1 liter is 1,000 milliliters times my volume or my molarity, which is 0.10 is what I have here. I have point 10. And
Right.
then point 10 is 1 mole of, I'm sorry, 1 liter of Na2CO3, and that
Correct.
will cancel out my liters. And then I did my 1 mole of sodium carbonate, and I did my 1 mole of calcium chloride, and I canceled out those units, and it gave me 96 milliliters times point 10 divided by 1,000.
Yes.
Okay, and then I got point 0.0096, right?
Yes.
Okay, so then I got that number, and then after I got that number, I was like, okay, now what do I do with that? So then I looked at this, and then it told me to calculate CaCO3 as well.
Yep.
And for that number, I got 0.02 because I had, where's my, is it, 100, it's still in my calculator, it should be, I'm not sure, let's see. Yeah, 100 times point 0.2 gave me 20 times, I'm sorry, divided by 1,000 gave me 0.02. Okay. Okay. Then that, excuse me. And then from there, I didn't know what to do with those numbers because the math just was really weird when I took sodium carbonate. I took my 0.096 and multiplied it by the 100.09. Should I have done the 0.2?
No. Okay. So two things. One, I'm going to ask you to close this part, and I'm going to ask you to close the lab data because I want you to look at the bottom. So on those two bottles, don't they both say 0.1?
These two?
Yes.
No, this one says 0.1, this one says 0.20.
Okay. All right. Then that's fine. No, you should that should have been what you did. You should have to multiply that 0.0096 times the 100.09, and that gives you a mass.
Yes, so when I did the 100, I'm sorry, the 0.0096 times 100.9, it gave me 0.96. Where is it? I'm sorry, I'm so stepping into the those. It gave me 0.960864.
Okay. And
But
what is that? What did
that
you just calculate?
I just calculated the mass. Or is that the percent?
Well, no, that is a mass, but what mass is it?
Sodium carbonate.
That's true, yes, but it has a specific name. So there are two things that you're supposed to be looking for. One of which is the actual yield, and one of which is the theoretical yield. Which one of those is it?
This is the actual yield.
That number that you calculated your expected mass of calcium carbonate, your
Mhm.
theoretical yield. So
Okay.
that's what goes into your calcium carbonate expected mass. That's right there under your limiting reagent. Not that one, the one below it. Yep.
Um, um, 4 sig figs. One, two.
I think it's gonna want to, but let's see what it says.
Okay.
Now, what's your observed mass?
96.
No,
Okay. Oh, the 0.0096.
no, that's your theoretical. That's what you calculate. That's not what we're talking about. Your observed mass is based on the mass that you measure. So your mass of the filter paper plus the precipitate minus the mass of the filter paper is the observed mass.
So 1.03 minus 0.21.
Correct.
Okay.
Now, how do we calculate a theoretical percent yield?
Times 100%.
Well, okay, but what times 100?
The 0.96.
Well, so percent yield is going to be your actual divided by your theoretical times 100.
So,
Because you want to compare how much you actually made to what you were supposed to have made and see what percentage that was. So it's your actual, which is that observed mass, divided by the expected mass times 100. So it's actual over theoretical.
okay. So 0.82 divided by 0.96
Done.
is 100. 85% yield.
That should be what they're looking for.
Okay. Oh, just saved it. Oh,
That's it.
that was hard. No, it wasn't.
It's a lot of figuring things out. So.
Okay. So on the synthesis quiz, is it gonna give me like these numbers here? It's gonna say you have this amount, this amount, this amount, and you need to calculate these.
That kind of thing, yes, that's what I would expect.
Okay. I need to save this. It usually lets you save these. I need to save them. I can't save. Oh, you have to hit print and save as PDF. Yeah, I'm gonna save this. Okay. I was like, I don't know what to do. And then when I tried to email you the picture, it wouldn't let me send you a picture in the D2O email.
No, it's weird.
It doesn't let you send pictures. So I had
It's
to
very strange.
put it in a Word document and then attach it. I was like, how am I gonna send this to her?
That way works, yes.
Okay, I think that is all my questions for now.
Okay.
I'm gonna work on the study guide tonight.
All right. And if you have anything about that, we can talk about that tomorrow or Friday.
Okay, sounds good. Tomorrow you are on from 12 to 2, right?
Correct.
Okay, sounds good. Thank you so much.
You are welcome.
Have a good one.
Thanks, you too.
Hello, Professor Hartley? Hello, Professor Hartley? Hello? Hello? My it would seem that my thing was off its kilter. Hello? Okay, can you hear me? Can you hear me? Can you hear me?
Of his personality, namely his immense anxiousness. He seems to be on the job. Roman Dissenza is a virus that is feared by the elite and the wealthy. While never mentioned in game, it is seen again below class specifically only the extremely rich of the world.
Man, what is going on with this mic? Hello?